Good day everyone. Welcome to another lecture of this lecture series on computer organization and architecture. So in this particular lecture we will be discussing about the paging. Okay. So in our last lecture we have briefly discussed what is paging and how it can be implemented. But this particular lecture will be the complete discussion, or we can say the detailed discussion about the paging scheme. So paging is a mechanism that helps us to implement virtual memory, or we can say it helps us to implement the memory virtualization. Okay. So we already know that in memory virtualization we are saying that when a process is allocated a memory, it is allocated, or we can say it is given an illusion. So it is an illusion kind of thing, illusion, or allocated the entire addressable memory. Okay, fine. So let's suppose this is our process P1, and if our addressable memory is 4 GB, then it is given an illusion that the entire 4 GB memory is allocated to this particular process, and it addresses that particular memory from 0 to 2 raised power 32 minus 1. Fine. This is virtual memory of process P1. Likewise, we will have a virtual memory for process P2 as well. Now this is a memory given to P1 and this is a memory given to P2, but we know that our physical memory, so let's say this is our physical memory. So our physical memory or main memory is the actual memory that is there in the processor, and let's say it is only 2 GB. And to run these processes P1 and or P2 at a time, we need that their particular data, or we can say their entire memory image. So this is the virtual memory image of P1, and this is the virtual memory image of P2. So we have to keep this image of P1 into the primary memory, and we have to also keep the image of P2 into the primary memory. But it is not possible to keep the entire virtual memory space of these processes into the primary memory, because we need two things. The first is there should not be overlap between these processes in the physical memory. Overlap means that one process should not interfere with the memory allocated to another process. Okay. The second is the size problem. Size problem means that it is 4 GB and this is also 4 GB process. How can we run a 4 GB process, or we can say how can we keep multiple 4 GB processes in a smaller physical memory? Okay, that is the technique paging that gives us the idea how we can allocate memory to multiple processes, how we can avoid this overlap problem and this size problem. So what is paging technique saying? This paging technique says that divide the virtual memory allocated to a process into fixed size blocks, and those blocks are called pages. Okay, and also divide the physical memory into fixed size blocks, and those blocks will be called frames. So these are the blocks of the physical memory and these are the blocks of the virtual memory, and you have to keep in mind that size of frame and page is same. So what I am doing here in the paging technique, if I have a process P1 and this process has this as virtual memory and this is another process P2, it also has its own virtual memory. We are dividing the virtual memory of P1 into fixed size blocks called pages. So here I have shown some page. For example, this is page 0, this is page 1, this is page 2, page 3, page 4. Likewise, this also is divided into pages, process P2. So it is page 0, page 1, page 2, page 3 and page 4. Okay, and this is our main memory. And this physical memory is divided into fixed size blocks which are called frames. So this is frame 0, this is frame 1, this is frame 2, this is frame 3. Let's say for simplicity, the size of these frames or pages is 2 KB. So the size of this particular page is 2 KB, or we can say every particular page has 2 raised to power 11 bytes. Or this also, every page has 2 raised power, every frame has 2 raised power 11 bytes. So 2 raised power 11 bytes means that to address a page, to address a byte inside a page or a byte inside a frame, how many bits will be required? So we will require 11 bits. And these bits will be to address a byte inside a page or inside a frame. And this is also called offset. So these 11 bits determine which page or which byte inside a page is required. Okay, so that means to access any item here in the virtual memory. So you can see that in the virtual memory, if I have a process P1 and it wants to access something, so process P1 usually generates an address. Okay, this address will be of some location inside this virtual memory, and this address has two parts. The first part determines which page number, and the second part determines the offset, or we can say which byte inside that particular page. This is also called offset. So offset will be of how many bits? 11 bits if the size of page is 2 KB. And page number, it is determined by this address. So if the address is 32 bits, so what will be the page number? How many bits? 32 minus 11, that is 21 bits. Fine. So this is how a address generated by a processor, which is a virtual address, is divided. It has a page number and offset. Now what I am saying that in the paging technique, we are dividing the virtual memory of processes into fixed size chunks called pages, and main memory is also divided into fixed size blocks called frames. Now what we are going to do, some pages of P1, we are taking those pages and placing those pages into the main memory, and the remaining pages are placed into the secondary memory. So let's suppose P1 is placed here and P2 is placed here. Okay, likewise some pages of P2, process P2, let's suppose page P3 is placed here and page P4 is placed here. Okay, fine. So P2 is in frame F3, P1 is in frame F2. Okay, P4, page 4 of P2 is in F1 and page 3 of P2 is in F0. Okay, so we know it, but to store this information, that which page is mapped to which frame. For every process there is a table which is called page table. So let's say this is the page table of process P1. Okay, this is the page table, and this is the page table of process P2. So first of all, we have to understand how many locations will be there in the page table. So page table is indexed by the virtual page number, or we can say page number. Okay, so it is indexed by the page number. So here you can see, for example, in this particular example, how many pages are there. So for a page number, we have 21 bits. So the total number of pages will be 2 raised power 21. So these locations will be 2 raised power 21. Or I can say that it is indexed by the page number. So for example, this is number 0, this is number 1, 2, 3, 4, 5, and so on. This is 0, 1, 2, 3, 4, 5. This is saying that page number 0 of process P1 is mapped to which frame. So you can see P2 is mapped to F3. So at 2 we will store frame 3, or we can say 3 means frame 3. Okay, frame number. Fine. And P1 is mapped to F2. So at one location we will store 2. Likewise, in the page table of P2, you can see P4 is mapped to F1. So at 4 we have 1, and at 3 we have 0. So you can see that in only these two positions we have a valid data. At other positions we have garbage data. Okay, to keep this track whether the entry contains the right value or the wrong value, or we can say the actual value or the garbage value, we have another part here in the page table entry. One is that it is storing the frame number, and it is also storing another thing which is called a valid bit. Valid bit says whether this mapping is valid or not. Not valid means that the page, for example, this particular one, here we have no data, so it is valid bit will be 0. Okay, valid bit 0 means that this particular frame page, so which page? Page 1 of process P2 is not mapped into the main memory. So that means this particular page is in the secondary memory. Fine. Now let's discuss this, how we can now access the details. For example, now let's say if our process P1 is running. Okay, if our process P1 is running. So let's suppose it generates an address. And we know this is a virtual address. And in paging, this virtual address has two parts. The first part is the page number. The second part is the byte inside a page, that is the offset. So now our memory management unit has to convert this virtual address into physical address. So what this memory management unit has to do, basically it has to see at which frame this page number is mapped, or we can say at which frame this page number of process P1 is mapped. So from this page number, we need a frame number into which this particular page is mapped. And to this frame number, we will add an offset. So this frame number and these 11 offset bits will give us the physical address. Okay, and how will this memory management unit get this frame number from the page number? So what it has to do, it will access the page table of P1. So because we know that this mapping, the page number to frame number mapping, is stored in the page table. Now in the page table, so this is the page table of P1. What this memory management does, that it will access this page table, okay, and it will see this particular entry, page number. So let's suppose this is this particular entry. In the entry, it will first see this valid bit. So if the valid bit is 0, if valid bit is 0, so what does that mean? It means that this particular page has not been put into the main memory. Okay, so if it is not in the main memory, where will it be? It will be in the secondary memory. So it means that there is a page fault. Page fault means that I am looking for an address in a page, but that particular page is not mapped into the main memory. So in the page fault case, what we have to do, we have to get that page from secondary memory and place in some frame of main memory, and also we have to update its page table, because now this valid bit will become 1, and here will come the frame number into which this page is placed. Then we can access this frame number. Now if valid bit is 1, valid bit 1 means that yes, this entry is valid, so that means this page is into the is placed in some frame, and from this we will get that particular frame number. So we will get frame number, and then we will concatenate to this frame number the offset from here, and we will return, this will be our physical address. These two together will be our physical address, and we will get the physical address. Physical address means the main memory address. We will access main memory to get data. Okay, so this is how the entire process of paging works. Now the thing is that when the page table of a process, this particular page table that our memory management unit is accessing, this page table is also stored in the main memory, this particular page table. Now if my memory management unit has to access the page table of a process, it should know where this particular page table is stored into the main memory. Okay, so in paging there is a special register called page table base register, and in this page table base register we store the starting address of page table in main memory. So where this particular page table is stored in the main memory, that starting address is stored in the page table base register. However, currently let's suppose I am running P1. Now let's suppose I have context switched. Now I am running process P2. So first here we were having the starting address of page table of process P1. Okay, now when I am making a context to switch, I have to update this PTBR. Now this PTBR will contain the starting address of page table of process P2 in main memory. So that means whenever we are making a context switch, we have to update the PTBR, page table base register. And if we are updating the page table base register, where are we storing this particular address which we are updating? Because we have to store it somewhere, and we are storing this particular address into the process control block of process P1, so that if the same thing is required again, we can easily get it from the process control block of a process. Okay, so this is how our paging works. Now let's see about this page table. So let's say I have a process P1. So let us calculate the size of the page table. I have a process P1. Let's suppose it has a virtual memory 4 GB. Okay, so what will be the address? So that means the virtual addresses will be of 32 bits. Fine. Let's say the page size is 4 KB. So what will be the offset? Or we can say, yes, what will be the offset? Offset will be 12 bits. Okay. Let's say I have a main memory of size 2 GB. Okay, so this 2 GB means how many frames? How many frames will be there? Number of frames. So each has size 4 KB. So number of frames will be 2 GB divided by 4 KB. That will be equal to 2 GB divided by 4 KB. It will be 2 raised power 19 frames. And you can also calculate number of pages. Number of pages will be equal to 4 GB divided by 4 KB. That is equal to 2 raised power 20 pages. Okay, so our virtual address will be like this: 12 bits for offset and 20 bits to access these 2 raised power 20 pages. So total will be 32 bits. Now we have to convert this into physical address, and you can see the physical address will be this page number. We have to convert into the frame number, and you can see that frame number is how many bits? 19 bits. 19 plus 12. So this will be our physical address. Now let's see what will be the size of page table for this particular process. So we know the page table of a process. How many entries will be there in the page table? So it will be the number of entries will be equal to number of pages. So how many pages are there? 2 raised power 20. Now you can see that what is there in the each page table entry. So in each page table entry we have a frame number. So you can see the frame number is how many bits? 19 bits. So 19 bits plus some additional bits. For example, valid bit is 1 bit. Another, there are some other bits also, for example, modified bit, replacement bit, but till now we are only considering the valid bit. Okay, let's suppose 19 plus 1, 20 bits. So what will be the size of this particular page table? Let's make it in a state of 20. Let's keep it 4 bytes. So yes, 4 bytes for simple calculations. Okay, so let's say every entry is of 4 bytes. So what will be the size of page table? One page table, 2 raised power 20 into 4 bytes. That will be equal to 4 MB. So let's suppose if I have 10 processes running. So what will be the size of all the page tables? It will be 4 into 10, 40 MB. So you can see the size is very large. So that means 40 MB of space in the physical memory is only required to save the page tables. So this is the single level page table. Okay. So what I am saying that 40 MB of space is reserved for the page tables in the main memory. Okay. Our aim is to decrease the size of page tables now. So we have already discussed everything, how virtual memory is implemented using paging scheme, what are page tables. Now we have to see how we can decrease the size of page tables. Okay, if I ask you the question, how can we decrease the size of page tables, one option is to use large page size. So let's suppose instead of 4 KB, I will use a 4 MB page size. So if you use a 4 MB page size, then do the calculations. You will see that the size of page table comes out very small. So it will be, I think, nearly equal to 4 KB. So from 4 MB, we are making it 4 KB. But the size of each page should be 4 MB. However, it has a disadvantage. So what is the disadvantage? Disadvantage is that means when I am placing some data in the main memory, I am placing a chunk of 4 MB. And in this 4 MB, there is a possibility that I am using only, let's suppose, 4 KB of data. The remaining data is unused. It is kind of creating a pollution in the main memory. Or we can say I am occupying the space, but I am not using the data that is present in that particular space. Okay, so this option decreases the size of page table, but at the same time it also decreases the hit rate of main memory. What is the meaning of hit rate here? Hit rate means that whether I am able to find the data in the main memory or not, because there is a possibility that some data is present in the secondary memory, and in that case that will be a miss in the main memory. Okay, so it means that from option 1 we can decrease the size of page table, but it has its negative effect. So we need some other solution to decrease the size of page tables, and the other solution is multi-level page tables. Okay, so we will discuss multi-level page tables, but first we have some other discussions related to page table that we will complete. Then we will go to and discuss multi-level page table. So let's say process P1 is running. Okay, now this process P1 has to access some memory. So it gives virtual address. So it has to access a memory. So it is generating a virtual address. This virtual address goes to memory management unit. And what is memory management unit doing? It will first convert this virtual address into physical address. And how it is converting virtual address to physical address? It goes, accesses memory to get page table of P1, because the page table of process is in memory, and it gets this page table of P1. From this page table, it will convert the page number of this particular address into frame number, and then it will combine offset with that frame number, and this will be our physical address. So after getting the physical address, then it will again access the memory. Which location it will access? It will access the location pointed by this physical address to get the data. Okay, so here we have, there may be a hit or miss. Those things you have to take care. I have not discussed those things here. Okay, so you can see that in this particular scenario, for getting data from memory, how many times we are accessing the memory? We are accessing the memory 2 times. Okay, first time to get the page table, and the second time to get the actual data. So this paging technique increases the number of memory accesses. So you can see that I was having to get the data from the main memory, but for every access I am making how many memory accesses? Two accesses. One for getting the page table and another for getting the data. Okay, and this will have the performance issues. And to solve those performance issues, we have a small cache inside the processor, and that particular cache is a special cache. Special cache here means that this cache stores the page number to physical page number to frame number mapping, okay, of most frequently used pages. Okay, so this small cache inside the processor, it stores the page number to frame number mapping of most frequently used pages, and this particular cache is called a translation Lookaside buffer. Okay, this is also called a TLB, translation Lookaside buffer. So what is a translation Lookaside buffer? So let me write it here. So what is the translation Lookaside So translation Lookaside buffer is a special cache inside a processor that stores the page number to frame number mappings of frequently used pages. Translation Lookaside buffer is kind of a cache. So it is basically a fully associative cache. Okay. And every entry contains the page number and its corresponding frame number and some extra bits. Extra bits are status bits. We don't have to discuss about the status bits right now because we will only discuss how this TLB is used. Page number and frame number of frequently used blocks. Okay, now let's see how it is improving the performance. So if I have a process P1, it generates a virtual address. Okay, so virtual address has two parts. One is the page number, another is offset. Now this goes to memory management unit. What this memory management unit does, the first thing is it will access the translation Lookaside buffer. It will access this cache. It will see if this page number, this particular page number, its mapping is present here in the cache. So it will search this cache. If there is a mapping available in the cache, it will get its corresponding frame number. Okay, so from the TLB, it will see if this page number mapping is there. If it is there, so there are two possibilities: hit and miss. Miss means that hit means that the frame number corresponding to this page number, that mapping is present in the cache. So if it is present, it will get the frame number, and to this frame number it will add the offset, and this will be our physical address. Then it will access the memory. So in this particular scenario, in this one, how many times we have to access the memory to get the data? Only one time. Now let's say this particular format. So let's say TLB and there is a miss. Miss means that the mapping of this page number is or this page is not in the TLB. Okay, so it will be a TLB miss. So in TLB miss, so that means now it has to convert this page number into frame number. That means it has to access page table, because in the page table there will be the mapping. So from this page table it will get the page number, and it will update this particular TLB with this new mapping, page number to frame number. Okay, so it will update TLB. So to this frame number it will also add offset to get the physical address, and then it will again access the memory. So in this particular scenario you can see that there are total 2 memory accesses. So having a TLB, we can decrease those extra memory accesses, but the only one thing we have to keep in mind that hit rate should be very high. Now the question arises is that do we have translation look aside buffer entries for every process, or we can say at a time are there multiple entries for multiple processes, or all the entries are belonging to a single process. So if my P1 is running process P1, then the entries in the TLB at that particular point all belong to process P1. Now if I am moving context to switching to another process, I will flush these entries and I will update these entries with the entries of process P2 from its page table. Okay, so that means at one particular point of time the entries contained in the TLB belong to one particular process, and if we are making a context switch, then we have to flush the TLB and update it with new entries. However, in some scenarios the TLB is not flushed. What does that mean? It means that the entry may belong to any process. For example, this entry may belong to P1, this entry may belong to P2. But how do we know which entry belongs to which process? So with every entry, we add another important information here that is called address specific identifier. And that address specific identifier says to which process this particular entry belongs. And in that particular scenario, when we are making a context to switch, we don't have to flush the TLB. Okay, so this is all about the TLB and how it is useful in improving the performance in case of accessing the memory. Now we were discussing about a mechanism to decrease the size of page tables. So how can we decrease the size of page tables? Okay, as I said, we discussed one option, but that option was not effective. The second option is to use multi-level page tables. Okay, let's see how multi-level page tables are working. So let's take the example of one single process. So this single process, let's suppose it has a virtual address, and virtual address is divided into following two parts. This part is the offset 12 bits, and this part 20 bits is the page number. So 12 bits means the page size will be 4 KB and number of pages will be 2 raised power 20. Okay. So this is our page table. Page table of P1. Now you can see that every entry here in the page table. So how many entries will be there? It will be 2 raised power 20 entries. Now in every entry there is one extra bit which is called valid bit, and for some entries valid bit is 1 and for some other entries valid bit is 0. Okay. Fine. So for most of the pages, for most of these entries valid bit is 0. 0 means that they does not hold any useful information. So they are not holding any useful information, but still they are occupying this space, this particular space. Okay, and we can easily get rid of these particular items, or we can say we can get rid of these particular entries which are of no use. How? For example, if I divide this page table, so let's say it has 1 2 3 4 5 6 7 8 9 10 entries. Let's say this is 0. So let me divide this page table into 5 different page tables of 2 entries each. So let's say this is one page table, this is another page table, this is another page table, this is the fourth one, and this is the fifth one. Now in this page table, this is the sub page table. So the first entry is valid, second is invalid. So here both are invalid, here also both are invalid. So here first is valid, this is valid and this is also valid, and here one is valid, another is not valid. Okay, so how many was there? So let's suppose address, this is 0 1 2 3 4 5 6 7 8 9, 0 to 9. Okay, now let's see. For example, let's take the example. If you can see that these two page tables, they do not contain any valid data. Okay. So instead of keeping a space in main memory for these sub page tables, I will not reserve any space for these two page tables. So here I have to reserve the space for all 10 entries. But if I am dividing it into sub pages, then I can easily deallocate these two sub pages and I have to reserve the space for only these three. These three means that for only those sub pages where at least one entry is valid. So here one entry is valid, here two entries are valid, one entry is valid. So for those sub pages where there is no valid entry, I will remove those pages from the, or we can say I will remove those page tables. These are page tables, sub page tables from the main memory. Okay, but now if I am getting, so now I am not using this address, this page table, I am using this as a page table. Now if my virtual address is like this, it has 20 bits, 12 bits, how will I determine which sub page I have to access? Because there are multiple sub pages, sub page tables. Okay, which sub page table to access? So I should know something, how I can access these sub page tables. So what we are doing, that when we are dividing this page table into these sub page tables, so for these sub page tables we require another page table, small page table. It will have total 1 2 3 4 5 entries. 5 entries here means the number of entries into which we have divided this particular page table. So this entry will store the base of this page, this entry will store the base of this page, this entry will store the base of this page, this entry will store the base of this page, and this entry will store the base of this page. Now in these entries it will again be a valid and invalid. So for these two pages it will have a invalid value. Invalid means that these two pages have not been created, and for other pages it will be valid. And this particular page, how many entries are there? 5 entries. So that means this particular address is subdivided into two parts. The first part will determine one entry in this particular page table. This is also called page directory. These are our page tables. So in the first part, we will get to know one particular entry here, and from this particular entry we will get which page table to access. For example, if it is saying this page table we have to access, now in this page table, which entry, the first entry or second entry, that is determined by the remaining bits, which entry to access in this particular page table. Okay, so this is how multi-level page tables are used. I will explain it with the help of an example again. Okay, and what is the advantage? The advantage is that the page tables, sub page tables that do not contain the valid data, those are not allocated in the main memory. So we can remove these two and we will be able to save some space. So only those sub pages are allocated in the main memory where there is some valid data. Okay, so now let me give an example. So here, how many levels we are making? So this is level 0, this is level 1, or we can say this is level 0, this is 1. Okay, so there are two levels, so it is also called a two level page table. So for example, if somebody says I will further divide this one also, okay, so then we have another page directory, so that will be a 3-level page table. Fine, so let's only stick to the 2-level page table. Let's understand it with the help of an example. So let's say I have a memory, virtual memory of 4 GB, and I have to create 2-level page tables, and page size is 4 KB, main memory is 2 GB. Okay, so what I am going to do, so I have to create a 2-level page tables. So my actual page table, if I am using a single level page table, the single level page table will be like this. It will be having 2 raised power 20 entries. Okay, so our virtual address in that particular scenario will be like this. This will be the page number, this will be the offset. Okay, and every entry stores, what is this entry storing? The frame number. Now let's say I am dividing this page number, I am trying to make a 2-level page table. Okay, so how can I make a 2-level page table? Let's say I am dividing it into pages, or we can say into page tables, sub page tables, where every sub page table has 2 raised power 10 entries. So every sub page has 2 raised power 10 entries, every sub page. So how many sub pages? So total entries were 2 raised power 20, and each sub page contains 2 raised power 10. So there will be total 2 raised power 10 sub pages. Okay. So we have sub pages here. So let me make on a new page. So our sub pages will be like this. These are our sub pages. How many sub pages? 2 raised power 10. Okay. And every sub page has how many entries? So it has 2 raised power 10 entries. So that means if I have to access one entry inside this sub page, so how many bits are required? 10 bits. Okay, and total how many sub pages are there? 2 raised power 10 sub pages. So that means to determine one sub page from these 2 raised power 10 sub pages, how many bits are required? 10 bits. So let's leave this one. So this will be the base address of this subpage. This will be the base address of this subpage. Base address means the address, or we can say the frame into which this subpage is placed, because every subpage is placed into the main memory, and in the main memory we have to place it into one frame. Okay, so the base address will be the starting address of that particular frame where this particular page is stored. So how many base addresses will be there? There will be total 2 raised power 10 base addresses. Why 2 raised power 10 base addresses? Because we have 2 raised power 10 subpages. And the base address of these subpages is stored in another table, which is called page directory. So this page directory contains, it contains the starting address of every page, of every sub page. So what will be the starting address? 19 bits, because it is a frame number. Okay, so this is our page directory. And in these sub pages we will allocate only those pages, only those sub pages where there is at least one entry which is valid. If all the entries in a sub page are invalid, we will remove that sub page, and for that sub page here the bit will be 0, valid bit. Valid bit 0 means that this sub page is not there, or this sub page table is not there in the memory, main memory. So that means we will be able to save the space. Now let's see how we convert virtual address into physical address. So what was our virtual address? 20 bits to offset. So basically this virtual address is divided now into 3 parts. This will be the offset, and these 20 bits, in these 20 bits the most significant bits will be required to address the page table directory. So how many entries are there in the page table directory? 2 raised power 10. So how many bits are required to access the page directory? 10 bits. So using these 10 bits we will access the page directory. Okay, so if I am getting these 10 bits, from these 10 bits I will first access page directory. So for example it is saying this. So from here I will get the sub pages, particular sub pages frame number, okay, or frame address. So let's suppose this is pointing to this particular sub page. Now in this sub page we have how many entries? We have 2 raised power 10 entries. Now which entry to access in these 2 raised power 10 entries? Okay, and that will be given by these next 10 bits. So using these next 10 bits I will access this sub page, and from here I will get the frame number, actual frame number. Now from this frame number I will add to this frame number the offset, and it will be my physical address. Okay, that is the multi-level page table. So you can see the advantage of this particular scheme is that we can save the space. How we can save the space? We will remove those sub pages, page tables where there is no valid data. But the disadvantage is that for every access, memory access, we have to do 3 memory accesses. Why 3 memory accesses? So first we have to access page directory. Page directory will also be there in the main memory. So that is the first access, plus then second time we have to access the sub page table, that is again in the main memory, another access, plus, and at the third time we will get this frame number and this offset, that will be the physical address, and using that physical address we have to again access the memory. So the total memory accesses will be 3, and that will be our disadvantage, and it will, this particular scheme will decrease our performance. Okay, so this was about the multi-level page table. Now there is another type of page tables which are called inverted page table. So we have an inverted page table. So in one level page table or multi-level page table, we were saying that there is a page table for every process. Okay. Why for every process? Because every page table is indexed by the page number, and page number, every process has its own page numbers, so it will have its own page table. Now in a state we can sort out this issue. We can have a single page table for entire processor. So here in this particular scenario we were having single page table for every process, but I am saying let's have a single page table for entire processor. So how I am doing that? Let's suppose we have a physical memory, and for example in this physical memory we have 2 raised power 19 frames. So we will create a table, so like this will be our table, and this particular table will be indexed by the frame number. So how many entries will be? 2 raised power 19. And we will say, let's suppose this particular frame number, here we will store which virtual page is stored in this frame number, this particular frame number, and to which process it belongs. Which virtual page is stored and to which process it belongs. So these two informations will help us to get the complete physical address. So let's suppose now the virtual address comes. So virtual address has how many parts? 2 parts. One is the virtual page number, second is the offset. So we have to convert this virtual page number into frame number. Okay, what in this particular scheme we are going to do? To this page table, to this particular inverted page table, we will send this virtual page number plus the process who has sent this virtual address, that is the process identifier, and we will search these two in these entries. So let's suppose I am finding these two entries here, virtual page and page ID. From here I will see the index. So index here, for example, it is saying 5. It means that this virtual page of this processor is stored at frame number 5. So I will get frame number 5, and to this frame number I will add offset, and this will be my physical address. Okay. So that means using a single page table, inverted page table, we can handle this address translation. But the issue is the searching. So we have to search each entry in the inverted page table to get the actual frame number. That is the overhead of this particular scheme. But we can sort out this, we can solve this by using some hashing techniques. So that will narrow down our search. Okay, but we won't discuss those things here. So this is all about the paging techniques and how paging is used to implement the virtual memory. So let me summarize what we have discussed. The first thing we have discussed is the paging. What is paging? And then we discussed how single level page tables are used to do a virtual address to physical address translation. Then we discuss what is a translation lookaside buffer and what are its advantages. Then after that we see the multi-level page tables, and at the end we have this inverted page table. Okay, so let me stop this particular video here, and with this we have also completed the discussion about the memory virtualization, or we can say the virtual memory. So let's meet in the next lecture. Till then, goodbye.